It's 3 p.m. We will wait for a while to see if people will join this class. We will start at 3:05. Hello, Karthik.
Good evening, sir.
Good evening. We will start in a while. Let's see if others will join.
Okay. Sir, I had raised some queries regarding the assignment questions.
Okay,
Nobody
so
has.
okay, they are not being answered.
No, sir. Almost 2 weeks. Fourth week, I had some doubt.
Okay, I'll note it down. I will uh, I will send an email to them to remind them about this.
Okay.
So for the fourth week, right?
Yes, sir.
Okay. Okay, let's start. So this
Yes.
is the week 6. I think uh, half of the syllabus is complete by now. We will have
Yes,
six
sir.
more weeks of classes. So, we will be solving questions about the Fermi-Dirac distribution. Till now, we have discussed the Drude model. We pointed out some flaws, and we try to correct them by now studying the Drude-Sommerfeld model. In the Sommerfeld model, main difference is that we use the Fermi-Dirac statistics instead of the Maxwell-Boltzmann statistics to improve the model.
Yes.
Here, so here, with the help of this new statistics, we can explain the anomaly regarding the specific heat. We can explain that, and also eventually we'll be moving forward to quantum mechanics. It's the first step because electrons are quantum materials, and so eventually we'll move moving towards quantum mechanics to understand our materials. So okay, let's start with the uh, first question. Fermi-Dirac statistics describes the distribution of what kind of particles across energy levels for systems in thermal or athermal equilibrium.
Fermions and thermal. Thermal. Yeah, D.
Yes, the answer is It's applicable to fermions because it's named after Enrico Fermi. So on him, the name both the Fermi Dirac and the fermions particles are named after him. Dirac is another scientist, and it's applicable for systems in thermal equilibrium. So let's discuss about fermions a bit. My screen is visible, right?
Yes, sir.
Okay. So fermions, so they are named after Enrico Fermi. And so there are some properties of fermions which is important to know. So first of all, so they obey, so they are quantum particles. So these are like so they are like quantum particles. So we will define in detail like uh, what should be the properties of a fermion. So the first one is that they should obey the Pauli
Exclusion principle.
exclusion principle. So what is the Pauli exclusion principle?
Police exclusion principle.
So what it
No,
says is
no two electrons can have all their quantum numbers being exactly the same.
yes at the same time, right? So what it says is that no two particles can occupy the same quantum state at the same time. So how do you define a quantum state?
Quantum state.
So for that, a quantum state can be defined by something called quantum numbers, right? So
I see.
we have discussed like in earlier like grades, like 11th, 12th, BTech.
Yeah.
So
The
instead of
number of spins.
yes, they have like something called quantum numbers. So how many types of quantum numbers are there? So there are
Azimuthal.
so there are four
Four.
quant four
Four.
quantum numbers. So first of all, it's the principal quantum number. So when we used to draw, you know, that there is a nucleus and there are like orbits, right? Just like n equal to 1, n equal to 2, n equal to 3. So these are the these are the principal quantum numbers. So it's also generally denoted by the number by the letter n.
Yeah.
And what they denote? They denote the uh, orbital size. Sorry, they denote the orbital size and the energy level. So because we know that all of these orbits of different size, right? This one, all of different sizes. The radii are different. Also, the energy levels are different for each of these orbits. The principal quantum number is the first quantum number that is used to define a quantum particle's state. And so we know that n like goes from so n should always be a positive integer. It's like 1, 2, and so on.
Yes.
The second quantum number is the azimuthal quantum number, or the secondary uh, quantum number. And it's denoted by the letter L. And this information that it gives is about the orbital shape. So what basically gives it subshells. And this L goes from 0 to n minus 1. So when we have that Hund's rule, this we have that this, like for example, the first quantum number we have 1s. For second quantum number we have 2s, 2p. So if you remember the shapes, then for the s and p it's different. Also p have like px, py. So all of them have different shapes. The px is a different shape from py, another. And so there are like three types of p. Why three types? Because uh, if you put n equal to 2, then L will be 0 and 1. So we'll discuss in detail. The third quantum number is the magnetic quantum number. And so this gives information about the orientation of the orbital. And this ML goes from minus L to plus L.
Okay.
And the fourth quantum number is the spin quantum number. So for fermions, they should be plus half or minus half. So it is a necessity that for fermions only plus half and minus half spins are can be there. If there are any more types of spins, then it is not a fermion anymore. For example, photons. So photons are not fermions because they don't have plus half or minus half spin. They have integral spins. So it's a very important for the fermion to have plus half or minus half spin. And the second, so this is the first criteria to define a fermion. And the second criteria is that this is also a quality of quantum particles, which is that fermions are identical and indistinguishable. So why it is indistinguishable? It is because we do not know the exact position of these quantum particles. Because last time we studied about the Heisenberg uncertainty principle, we saw that there is a error in the position of the. Can you please mute your microphone?
Yes, sir.
There's a lot of background noise. Okay, so last time we discussed that in the Heisenberg's uncertainty principle, that there is an error in the position of the particle. which is a fundamental error. The result is indistinguishable is because the exact position of quantum particles or which of fermions, which are quantum particles, is not known. We only know where the probability of finding particle is high. So if we do not know where a particle exists, we also cannot talk about what will happen when two particles will come together and what will happen to them post meeting, because we do not even know which particle is coming, where it is located. We only have a probability, so we cannot distinguish the interactions, distinguish particles after interactions, and so we say that the fermions are identical and indistinguishable. So this is the definition of for fermion, and the Fermi-Dirac statistics, as the name suggests, is applicable only to fermions, and and it's supposed to be in thermal equilibrium. That is how we. That's why we have temperature dependence of these particles. If it was an athermal process, then we wouldn't observe any temperature dependence. So this is the definition of fermions. This is how we uh, define fermions. There are other particles also. There are other quantum particles called bosons. They have integral spin, for example, photon. Even this is a quantum particle, but the Fermi-Dirac distribution is no more applicable to this. What we have is Bose-Einstein statistics. So we'll move to the next question. If the total number of particles in a system is not fixed, then system energy can keep on varying. True or false?
It's true.
Yes, the answer is true. So when we write the total energy, the system energy, it is a summation of like over summation over all energy levels. So it's like energy level EI and the number of particles with energy level. So the energy. So if we change the number of particles, then obviously the system energy will change. So answer is true. So if we do not have this formula, we can also just draw if we let's say have several energy levels, E1, E2, E3, E4. So if let's say we have like two particles at each energy level. So if we add or remove a particle, then the system energy changes. If we remove a particle, then again the system energy changes. And so the answer is true. With the change in the number of particles, the system energy can vary. If we increase the number of particles, then system energy will increase. If we decrease the number of particles, then the system energy will decrease. The third question is, the general probability in Fermi-Dirac derivation depends on only the conditional probability only the probability of finding the state at n bar. The difference between the conditional probability and the probability of finding a state, microstate n bar, or the conditional probability, as well as the probability of finding the macrostate n bar.
D, sir.
Yes. So both of these are important. Both the conditional probability and as well as the probability of the probability of the system to be at the microstate n bar is important. So there are like three terms here. So one is the energy, then there is the state, and then there is this electron or particle. So there can be different energy levels. Like E1, E2, so forward like EI, and each of these states, each of these energy levels. So these are the energy levels, and each of these energy levels have some states in them. We will not currently we won't discuss about how many states are there. We'll just say that okay, these energy levels have some states in them, and the number of states is given by, let's say, the letter S, S1, S2, Si. So the energy level EI has Si states, and then it can occupy some particles. So let's say the Si state has Ni particles and it can occupy some positions. And so there are Ni states, sorry, Ni particles, Si states. So Ni particles can be arranged in Si number of states in the energy level Ei. And so if you try to write, and then there are two things. One is the conditional probability, and second is the probability associated with the state being at the for finding a microstate n bar, which is the most probable microstate. And so first of all, the conditional probability, it's denoted in this fashion. So what this means? This means that this denotes the conditional probability. So it's a conditional probability that the state entry level is occupied particular microstate n1. So this is one particular microstate. So in this microstate, the Ni particles are in SI number of states, and these are the positions in which these particles are located in this particular microstate. Now, along with this, we have to also find what is the probability of this microstate. So this is the probability that system is at the microstate n bar. And so we also know that the most probable microstate is also the equilibrium microstate. And so now if we write the equation for the general probability, Fermi-Dirac distribution, this is general probability of finding like probability of a state being filled in energy level E can be given by the, first of all, the conditional probability. This is the conditional probability that a state in energy level E is occupied, and the probability of that state existing. This has to be and this has to be done over all microstates. But if you would have gone through the derivation, you will see that since only one of these microstate is the most probable one, the summation is not actually important, because you will see that probability of only one state will be very high. So we can remove the summation, and only the most probable state will be considered. And the way you calculate this probability is by, so this is the number of ways. Let's denote by, I think in the book it's omega. So this is the number of ways in which the microstate impact can be obtained, and this is the all the number ways so eventually there will be only one macrostate which has to be considered, and so this thing will be close to 1 in a large system. So that is what eventually will happen, but this is the general equation. This is the general probability equation, and so it has two terms. The first term is the conditional probability, which is this term, and second is the probability associated with the state being at n bar microstate, which is this entity. Okay, so let's discuss the next question. So Sommerfeld, or the Drude-Sommerfeld model, it is known by both names. So the Sommerfeld model improves the Drude model by implementing the concept of implementing which of these concepts? Identical, indistinguishable. Can you repeat? Sorry.
A and C, identical and indistinguishable, and also fermions.
Yes, yes, yes. So yes, so basically it's as we discussed in the first question. The Drude-Sommerfeld model considers that electrons are both identical and indistinguishable, and they are fermions. So there are two models: the Drude model, the Drude, then there is the Drude-Sommerfeld model. So in this case, in the Drude model, the Maxwell Boltzmann statistics was followed, and in this the Fermi Dirac statistics is followed. And so these are fermions, and so the answer C is correct first of all, because the Fermi Dirac statistics is included. And secondly, let's discuss about uh, the identical and indistinguishable concept. So in the case of Drude model, the Sommerfeld model, so let's say we have two energy levels, EI and EJ. So if there are like two particles here, and this comes here and this goes here, so the particles swap their position. So in the case of in the Drude model, so since the particles are identical, sorry, are distinguishable, since they're since the particles are distinguishable, so swapping leads to a different microstate. Whereas in the case of Sommerfeld model, since they are indistinguishable, so swapping, so it does not lead to a different microstate. So this is where the importance of indistinguishable particle comes, and it's both identical. So it's for both of them, for both Drude model as well as the Sommerfeld model. The particles are identical. So even though swapping, so in both of them, swapping does not cause change in total energy, because even if they move their positions, the net energy of the system remains same. It's a summation of total energy is given by number of particles in each energy level multiplied by the energy level, the summation of all this. So this energy, this remains same. This is the importance of the term identical, and this is the importance of the term distinguishable and indistinguishable. So this one more thing. Okay, so this is why even the first, this is also a difference. In Sommerfeld, we have indistinguishable particles. Okay, let's discuss it here only. So there is all the statistics leads to one major difference. So uh, in the Drude model, so there is no upper limit to the number of particles at each energy level. Whereas because of the Pauli exclusion principle in the Sommerfeld model, there's an upper limit to how many electrons can be there at each energy level, which is also very important. Which is why we would see that in the Maxwell-Boltzmann, uh, if you cool down the system, then all the particles can go to lower energy level. But that doesn't happen for the Fermi-Dirac statistics. So I will write it down here. So this is for classical particles. I think I have already mentioned it. So what we see here, the number of particles at any energy level is not subject to any specific upper limit. So there's no upper limit in the case of Drude model. In the case of Sommerfeld model, so this has fermions which follow the Pauli's exclusion principle, because of which the number of particles is limited. By the number of states available and so in this case, the number of particles is limited. That how many particles can be there at an energy level, and that is limited by the number of states at that energy level. And so, which is why if you see a distribution, even at very low temperatures, you will find in the case of Fermi-Dirac distribution that the particles are filled up to a much higher energy. We will discuss about these plots, how do they look like in the subsequent questions. So the Sommerfeld model says that it's applicable, the electrons are fermions, and so we have to apply Fermi-Dirac distribution, and they are identical in indistinguishable particles because they are quantum particles. This is the next question. Constants placed on the system while deriving the Fermi-Dirac distribution function are total energy and total pressure of the system, total energy and number of particles in the system, total energy and a fixed number of available states in the system, total energy, number of particles, and fixed number of available states in the system. Any answers?
B, sir.
Can you repeat?
B.
You are saying this one?
B. Total energy and number of particles.
Yes, yes, yes. So you're correct. The answer is B. So we place the constants. So what are the constants? The constants are the total number of particles, so total energy and the total number of particles. So let's. So total energy. So we say that the total number of particles in the system is a constant, and we say that the total energy is a constant. So EI is the energy level, and NI is the number of particles at that energy level. So these are the constants that we put in, while we derive the Fermi-Dirac distribution. So next question is the number of states occupied by the electrons, their energy and density of allowed states in the allowed state is the information which can be obtained from the probability of occupancy versus energy plot of Fermi-Dirac distribution at the absolute temperature. So basically, can you find the number of states from the probability distribution function?
No.
No,
Density
sir.
of states.
So you didn't understand the statement?
Yes, sir.
Okay, so we have this formula, right, for the Fermi-Dirac distribution. So this EF is the Fermi energy, and this is the distribution. So can you can you give an information about the number of states from this distribution? So what is this function? So if you would have seen earlier, so we have discussed somewhere here. Okay, we just mentioned the general probability here. Okay, so this is this is just the probability of the state at energy level E to be occupied. But okay, so the answer is okay. Let's discuss in detail this question. So what we get here. So let us first define this. So what is this thing? So uh, this function gives us information. So this is a probability function about the probability of occupancy of states in the energy level E. But can you say how many states are at that energy level E? So the question is,
No, sir.
how many states are at energy level E? So as you said, so we cannot say that from just this function. So from this function from Fermi-Dirac, we cannot comment, right? So the answer is false,
False.
because
False.
false. Yes, answer is false. So because FD does not give any information. Regarding the number of states. So if you want to find out that how many states are there, so that is what we want to find out. So if we want to find out the number of occupied states, so we have to multiply this probability with the number of states available at energy level E, right? So we know how many states are available, and then we know what is the probability of that state being filled. That's how we can know the number of occupied states. You got it?
Yes, sir.
So if let's say there are like 10 states available at energy level E, the probability of finding it is like half, then we have 5 occupied states, right? By the way, where will this like where will it be half? It will be half at the Fermi energy. I think we have that question later also. So this is half at the Fermi energy. I think we have that question. If not, we'll solve it. We have that question. So the electronic contribution to the heat capacity at constant volume of the classical model. Classical model is in as in the Drude model is corrected by applying which of these models?
B and C.
Yes, right. So basically these two are related and these two are related. And so the answer is both B and C. So I think we had discussed this question in the lecture number 4 also. So I'll write down the equation again. The Fermi-Dirac distribution is given by 1 plus exponential E minus Fermi energy by Boltzmann constant into temperature. Now if you plot it, this is the energy and y-axis is the probability. So you will notice one thing. Okay, I'll write it down properly. That in the case of Fermi-Dirac distribution, we hit the value of 1. We hit the value of 1. So this is because, as we had discussed earlier, so we have this Pauli exclusion principle, and so the number of particles at any energy level is limited by the number of states, whereas in the case of Drude model, there is no specific upper limit. So there's no probability like of 1 as such in the Maxwell-Boltzmann distribution, like we have in the Fermi-Dirac distribution. And so this is at t equal to 0, and when you heat up this system, this would be it should exactly coincide, and they will intersect the half position. This actually looks more like this. So now if we consider the transitions, if this is the plot, if we consider the transitions, so if there's any state here, it cannot jump to this state because it is already at 1, the probability is already 1. So this transition is not allowed. So this is not allowed. Why? Because there is no space here. But if there is a particle here, it can take energy and jump here. Electron here can gain energy and jump here. Gain energy and jump to higher energy level. So these transitions are allowed. So what it means? It means that only electrons in this regime, only they can absorb electrons. Only they can absorb energy. Absorb energy. And how do we define the specific heat? The definition of specific heat is, or the heat capacity, the specific heat capacity. So the definition is the quantity of heat absorbed per kilogram or per kg or any unit mass of material to raise its temperature by 1 degree Celsius. So in the case of for the particles, for fermions, so for the case of fermions, only the shaded, so a very less number of electrons participate. In the case of fermions, only few electrons participate. Whereas in the case of the classical particles, which follow the Maxwell-Boltzmann distribution, all electrons participate. And therefore, it's easier to increase temperature in the case of fermion. and that's why, and that is how we were able to correct the 100 times difference between the observed specific heat and the calculated specific heat is in the Drude model. So we'll move to the next question. I think the other questions are easy, so we'll finish in a few minutes. So according to the Drude model, which was derived using Maxwell-Boltzmann statistics, which of this is correct? So in the previous question, we discussed about the fermions, and this is for classical particles following the Maxwell-Boltzmann distribution. Any guesses? Any suggestions?
Yes.
Yes. So A is correct. All particles can gain energy. And also along with this, also this D is correct. So if you plot this, so this is like, what is this? This is energy, and this is the number of particles. So initially, if we have a plot like this, okay, I've drawn it very bad. So this was the initial at, let's say, T1, and if T2 is greater than T1, what will this plot look like? This plot will look something like this. T2. So in this case, if you look here, so in the case of T2, more particles at higher energy, right? This is number of particles, and at lower energy levels, less particles at lower energy. Why is this so? Because all the particles have gained energy, and they have like moved from right to left. And so we have now less particles at lower energy and more particles at higher energy when we increase the temperature, because all particles have gained energy. And secondly, so we can now write by the equipartition theorem, like, this total kinetic energy is equal to the 3/2 3/2 kT, right? You remember this equation we had also used this when we were discussing, when we tried to find out the specific heat in the case of classical particles in the Drude model, when we considered electrons bouncing off walls. So if the temperature is increased, then this entire value is increasing, and so also the kinetic energy increases. So the kinetic energy of all particles will increase with the increase in temperature. You got it, Karthik?
Yes, sir.
Okay. Okay. So at the Fermi level, what is the probability of occupancy?
is 0.5. Put the point.
Yes, so we have drawn it earlier. So the answer is equal to 0.5. If we again draw it for future reference. So if this is the Fermi level, this is the probability. This is like half position. Then this will go like this. You can also solve for it. The Fermi Dirac distribution. 1/1 plus epsilon. Sorry. Exponential e minus f by kt. So what happens to this term at e is equal to ef?
0 by t. T is
So sorry, this
positive.
is so this case. So t is greater than 0.
E to the power of 0 is 1.
So it's 1. Basically
Yeah.
1 by 1 plus 1. So it's like 0.5. So at Fermi energy, probability of occupancy is half. And we have 2 questions, but let's just solve one question. We can take our next question in the next class. So total number of ways for distributing 5 particles in 10 energy states with 1 particle per state is calculated using which expression?
B, sir. Psi factorial NA. Sorry, C.
Which one?
D, I think. Si factorial by Ni factorial into Si minus Ni.
This one?
Yes.
Yes, you're right. So since the particles are indistinguishable, so the order of particles, so the arrangement of particle is not important. So that is why we will use a combination instead of permutation. So it's like a combination of Ni, so which is like 10C5. So this is 10 factorial by 5 factorial by 10 minus 5 factorial. Not calculate, or Si factorial by Na factorial Si minus Na factorial. Okay, it's capital N, not a small n. Okay, so answer D is correct. Okay, so I think let's stop here. We'll solve this question next time. It's already 1 hour. So okay. Okay, Karthik, I will send an email to the other TS asking them to go through your doubts in the 4th assignment.
Yes, sir.
Okay, so you have any questions from this class, or it's fine?
I had a couple of them. Okay, we can discuss in next.
Okay, you can ask me. You can ask me.
So the same thing. I think they have taken one problem no, in the end. That is from the textbook what the sir has authored.
Hello.
Yeah, the problem what you were about to discuss.
This one.
Last one, yeah. That is from the same textbook which
Ha
the
ha
sir
ha.
has authored. Yeah,
Yes, yes, yes,
physics
yes,
of
yes.
materials. Yeah,
Yes, yes, yes.
in the same book he has given from multiple choice questions. So in that a couple of them I had doubts. So that I wanted to clarify.
Okay, so I think you can write it up in the discussion
Forum.
forum. That is
Okay.
what So your classroom TAs should be able to help you with that.
Okay, sir, but they take a lot of time to respond. That is a problem.
Oh, okay, I will send them an email. Don't worry. I will send them an email.
Okay.
I will also send an email to professor also,
Okay.
so that he gets to know that the questions are not being answered.
That is for assignment 5, not so for 4. Sorry. That's what I told.
Uh-huh.
The query that I have raised is for assignment 5, not for 4.
Okay, no problem.
Yeah?
So
Okay.
basically, I have been asked to not solve the assignment questions in the class
Okay.
because
But
so I may give you an answer here. It will be on YouTube, right? So others may be able to just like look at the video and then answer the assignment. So
no, yeah.
so don't worry.
There,
I will let the people know too. They will personally help you with this
okay.
assignment.
But we are discussing the questions for which the due date has passed, not
Okay.
the present. So that's why.
Okay. Okay, Karthik.
Mm.
Uh, I think we can stop here.
Sir, next